Right. I am genuinely impressed how many of you made it out today in this extremely snowy day. So well done, everyone. Okay, a couple of notes. One thing to note is that there's a test coming up 2 weeks from today. It will be in this room. I'll post an announcement about this. Unfortunately, we'll be in this room. To prepare for the test, as promised, I put some blank derivation pages on Quarkus. And I just want to remind you that practicing pen and paper is absolutely crucial to doing well on the test. If you do all of your practice on Logic 2010, you will be in deep trouble. That will not work out for you well. You will be baffled as to why you thought you could do logic and then you can't anymore. The answer is because you only practiced on Logic 2010. So the blank derivation pages that I've included are exactly what the test pages are going to look like. So you can practice every aspect of writing the test except being in the exact test circumstances. So print a bunch of these. Here's my recommendation. Print a bunch of these off and practice your derivations. Practice the derivations for the exercises that are assigned and practice derivations that aren't assigned on these pages. Okay? It's my strong recommendation for how to do well in the test. Yeah?
Are you gonna post the answers to those questions just so we can go back and check our work to make sure that we're
Well, for any derivation that you're pulling off Logic 2010, you can type the answers into Logic 2010 and it will tell you if you did it right. Yeah? Okay, good. Good. No, I'm not going to just post like a million derivations on, yeah. Another question.
Yeah, how much time per question are we going to have?
So there's going to be, the test will consist of, and I'll post more as we get closer to the test. The test will consist of 6 symbolization questions, 4 derivations, and some truth tables, and some short answer questions. So there's a fair bit. It's a 2-hour test, so you got lots of time to deal with this. This is the same length, the same number of questions as I gave last semester, and people found that there was not an incredible rush to get it done. About half the class was done before time. So it's not an incredible rush, but you do have to practice enough so that you get fluent in this stuff, so you can knock them out reasonably quickly. Yeah? So I don't know how to break that down into number. Some people take more time on symbolization, some people take more on derivation, so I don't know how to break that down into time spent per question, but that's the breakdown of questions. Other questions? Okay, good. So exercise 3 is posted. And as of today, you will have all of the skills to deal with all of these questions. So these questions are all, except actually the first 2 you could probably solve right now. But the remainder, I'm going to teach you what you'll need to know to solve them today. So next time we'll do what are called derived rules. I believe none of these require derived rules. We'll deal with derived rules next week. Okay? Okay. Before we get into really new material, before I introduce a bunch of new rules, I want to talk a little bit more about show lines and just highlight a couple of things that you can do with show lines. So last time the things that we can do included, I pointed out that if you've got a conditional, so suppose you got in one of your premises a conditional, it's very often helpful to write a show line for the antecedent of the conditional so that you can use modus ponens. So once you've shown the antecedent, you can do modus ponens that premise and get the consequent. Or it's often also helpful to do the negation of the consequent, and then you can use modus tollens and get the negation of the antecedent. So those are the 2 things that I showed you that you can do with show lines last time. Now let's just do a couple more things that show lines are handy for. For example, building yourself a conditional is one of the things that show lines are really, really helpful for. So given something square, you can get any conditional of the form if circle, then square. And given not square, you can get any conditional of the form square, then circle. let me show you the derivation that makes this, like how this works in terms of derivation. So I'm going to show you two derivations now where we prove that this is true. And I hope that these derivations are examples of a kind of a short set of moves that you can make really anytime you want a conditional and you either have the consequent or you have the negation of the antecedent, you can get that conditional for yourself. So let's do those really quickly now. Okay. So this is an example of, so this is Theorem 2 from Logic 2010. And this is an example of, so if you have square, then you can get any conditional of the form if circle then square. Right? So Q is our square here, and if P then Q is our if circle then square. Right? So this is an example, this derivation is meant to be an example of how you can get, and notice how it doesn't matter what Q is. Q could be some big complicated thing, it doesn't matter at all. So let's do this derivation. So, thing to show is if Q, then if P, then Q. Okay. And we can assume Q for conditional derivation. So that's our, we have square, right? We have Q. We've assumed it for conditional derivation. Now we need to show if P then Q. So in a derivation, suppose you wanted to build a conditional, you wouldn't necessarily know that this might be a show line that you spontaneously have to write. So suppose that you just, all you know is that you want if P then Q, and all you've got is Q. Then you can, unprompted, write yourself a show line, and then you can assume the antecedent for conditional derivation. You want to show Q. Well, that's showing Q. Given that we have Q, showing Q is pretty darn easy, right? You say 2, repeat, direct derivation, and that's it. We brought line 2 down into this. That was the thing we were trying to show, so we did a direct derivation of it. And then we can just close off our derivation. So on line 5, we did a conditional derivation. Okay, so the lines from 3 to 7 are the main thing that I want you to see here. The lines from 3 to 7 are where basically you started with Q on line 2, and then you built the conditional if P then Q just on the basis of having Q. You didn't need anything else to get this done, right? So kind of not out of thin air, but just on the basis of having the consequent of that conditional, I could build the conditional. And P could be anything. Okay, just for the sake of completeness, I'll close this off. It'll just bother me if I don't do this. Okay. Okay, but do you see how this is given anything square, you can get if circle then square. And you get that by writing yourself a show line for if circle then square. You get to assume circle, and then you just bring square down into the derivation, close off the conditional derivation, and you get the conditional. Yeah?
If it is in the test, do we need to write down the huge bracket and also cancel line?
The huge bracket?
Yeah, the boxing.
You need to do all of this box. Anytime you write a show line, you have to do this box and cancel thing. Yeah, yeah, for sure. For sure. So, okay, again, imagine that this wasn't the thing that you're trying to show. All you know is that you've got Q and you wish you had if P then Q. The lines from 3 to 7 are basically the important part of this. Okay, and it's just a thing that you can do with a show line. Okay, let's do another. Let's do the other one. So this is Theorem 18. for question 118 from Logic 2010. And it's the same basic idea, except in this case we have not box, and what we want to get is if box, then circle. And again, circle could be anything, anything. So show not P, then if P, then Q. I'm going to assume not P for conditional derivation. I'm going to show if P, then Q. Okay. So we started with not P, which is our not blank, not box. We want to show if box, then circle. We started with not P. We want to show if P, then Q. So if you've got not P, let's say to repeat, not P, and once you started this show line, you got to assume for conditional derivation, the antecedent, you got to assume P. Now we got P and not P, as we can say 6, 7, ID. It shouldn't bother you that P and not P is how we close this thing off, despite the fact that we're trying to show Q. Doesn't have to be a contradiction with Q. It can be a contradiction with any contradiction you find is enough to close off the show line. And now we've done it. We've basically done the derivation. So on line 5, we did a conditional derivation, box and cancel, which means that on line 3, we did a conditional derivation, box and cancel. Okay. So again, things to note here. I mean, I'm doing this with the simplest possible versions of this, just if not P and trying to show if P then Q. That not P could be not if P then R or W. Like it could be some big complicated thing. But if you've got the negation of anything, be it simple or complex, then you can get that thing unnegated, then anything else. So you can build very complicated conditionals this way, so long as you've got either the negation of the antecedent or the consequent. So the first derivation I showed you was when you have the consequent. This one was when you have the negation of the antecedent. So is this going to come up a lot? Not a lot, but these are moves that you can use unprompted show lines. So the structure of these derivations made these show lines kind of prompted, but the thing just to remember is, if you find yourself in a position where you've got not P, you can always write yourself a show line if P then anything and get that thing just on the basis of having not P. So all the moves throughout here, all I really required was having not P. So these are conditionals that you can build for yourself. Okay? Okay. So just for some clarification, in Logic 2010, there's a rule called MC that you can do those derivations in just one step. There's a rule that says if you've got not P, then you cite that line and say MC, and you can get if P then Q. We're not going to use that rule in our system because basically it just saves you about 3 lines in a given derivation, and I want to keep the system that we're using as simple as possible. I want to keep the number of rules that you're working with as low as possible. And so I'm going to include a few. So on Wednesday, we'll do some derived rules, which can save you sometimes like 30 lines. These ones save you 3 lines. So we're not going to include MC. It's not going to be a rule that you're allowed to use. But I did want to show you how you can do this, the same work as MC just using show lines creatively. Okay? So that's the first thing I wanted to show you, thing that you can do with show lines. Any questions about this? I mean, the moral of the story is that show lines are great. And if you find yourself stuck, you should keep in mind that you've got them as a tool. If you find yourself wishing you had a conditional, and you have part of the conditional, try to think if you can make either of these moves. Okay. Here's one more thing that you can do with show lines. Let's call them contradiction generators. So one of the really common ways of closing off a derivation or a subderivation is to find a contradiction. And another thing that you can use show lines to do, these unprompted show lines, is to write a show line for the negation of something that you have. So I've got not P, or not something. I write a show line for the opposite of that. And if you can close that show line off, if you can finish it, then you have a contradiction, and your subderivation or your derivation is over. You've finished it. Okay, so sometimes you'll have something and you're not sure how to use it. Have this thing. I don't know what to do with it. I don't know how to make it into something useful for myself. One of the ways to make something like that useful, if you have it, is to use it to generate a contradiction. Write a show line for the opposite of that thing, and if you can close it off, then you've used it to generate your contradiction. So let's do an example. So this is derivation 1.025. Okay. So I'm gonna start this derivation and I'm gonna get stuck. Watch me. And I'm planning on getting stuck this time. All right. Okay. So show if not P, then Q. Great. It's a conditional. Anytime you're trying to show a conditional, we start a conditional derivation. So we're going to assume not P. And we're going to show Q. And I'm going to start, because I'm trying to show something that's not a conditional here, I'm going to start an indirect derivation. OK. So set up my show lines. Now I'm going to do a survey, standard derivation procedure, to do a survey of what I've got available. What have I got? What can I do with it? So I've got lines, currently lines 2 and line 4 are available. And I got my premises, 1 and 2. So now I should be casting around, trying to see if any of my available lines fit together with any of my other available lines or my premises to do something useful with. So without even, at this point, I'm not even kind of thinking about my end game. I'm just looking for obvious opening moves to kind of free up some possibilities here. So for example, line 4 and premise 2. Hey, there's something. So I can say line 4, premise 2, modus tollens, give myself S. Once again, I'm allowing myself to give myself the double negated version of this because you can choose what you get. It had to be not Q at the beginning. Anyway, okay, so, okay, all right. So I've got S. That's fun. That's good. Any other obvious moves that you see? 2 premise 1 modus tollens. Good. So now I get, it's not the case that R, if R, then S. Oh. Good. Very good. Now, On Wednesday, I'm going to introduce a rule that we could use line 6 with. So the negation of a conditional will eventually become useful to us, but only if you're allowed to use these derived rules. So 2 of the derivations on the test will be basic rules only. We're not allowed to use the derived rules on those first 2. So line 6 is not super helpful for us on the face of it. Like it doesn't look like, there's not much you can do with a negated conditional in the basic rules system. Given the rules we've got so far, it's not super helpful. Okay. However, we can use line 6. Line 6 is going to be useful in this derivation. Let's use it to generate a contradiction. So what would be nice, what would let me close off this derivation, is if I had a contradiction. Any contradiction will do. But in this case, I've got something. It's the negation of if R then S. If I could, for example, show if R then S, yeah, then I would have my contradiction. So I'm going to assume R for conditional derivation. Try to show S. Yeah. Isn't it the same as assuming an indirect derivation? Well, I can only do an indirect derivation. I can only start an indirect derivation right after a show line. On what line would I have done that? No, I cannot start an indirect derivation in the middle of a subderivation. It has to be right after a show line. Yeah? Okay, that's one of the rules on when you can start an indirect derivation. It must be immediately after a show line. So yeah. Okay. But now I'm close. Now I'm close to being able to sort this thing out because I want to show S. Well, the good news is that I have S. So I say line 5, repeat direct derivation. I've shown S. Now, on line 9, I did the conditional derivation that I started up here. And I've shown if R then S. Please note that this is the exact thing that I suggested to you just moments ago, where if you've got the consequent of a conditional, you can build the conditional by writing a show line for it. Do you see what I did there? So I had S. I can get if R then S on that basis by writing the show line, show if R then S. So that's the skill I just showed you a couple minutes ago. But this time, the reason why I wanted that conditional is to generate a contradiction. The reason why I wanted if R then S is because 6 and 7 are now exact opposites of each other. So I can say 6, 7, ID, indirect derivation, and close off this. Yeah? And having closed off that, of course, the derivation is over. So I've showed on line 3, I did a conditional derivation. Box and cancel. Okay, so what I did there was try to produce a contradiction with something that I have. Probably better not to just try to produce a contradiction out of thin air. You should have 1/2 of it already. You say, oh, what am I going to do with this 6? Like line 6. I'm like, what am I going to do with line 6? I have it. It's a resource for me, but I don't see how to translate it into something that's going to be useful. One way of doing that is to write a show line for the negation of something that you have and thereby generate the contradiction. Now, it's got to be a show line with all of these show lines. It's got to be something that you think you have some hope of maybe accomplishing. Because you can't just, if you've got an open show line, you can't complete the derivation until you've finished it. So don't start just writing show lines at random. You got to write some for them for something you think you can show. But in this case, we could show it because we had S. Okay? The magic of show lines. They're wonderful. And again, you can tell it's time to write a show line because they're like the midlife crisis of a derivation. Okay, the show line is like a midlife crisis. You've accomplished all the obvious goals, you've done well, you have lots of assets, but somehow you're not getting to the final thing. And now it's time to produce for yourself a new goal. You generate, kind of out of thin air, a new goal, and if things go well, that new goal will get you to take up photography or something, I don't know, whatever you plan on doing with your midlife crisis. The new goal opens up new possibilities for you, which can then get you to where you're trying to go. Okay? Any questions before I move on to kind of newer stuff? Great. Okay, so the magic of show lines. The emotional signal that it's time to write a show line is that you don't know what to do next. You're lost, you think you've done something, so you've searched through all of your assets, you've used as many as you think you can, you've done all the automatic moves, you've done all of the things that are obvious, and nonetheless you're stuck. That might be time to write a show line. And so it's a kind of stuck feeling that's your signal to start looking out for show lines that maybe would be helpful to you. Okay. But keep in mind not to do the following. Don't write a show line for premises. Don't write a show line for available lines. This happens a lot, actually. I've marked a lot of these tests. People will write show lines for things that they have, and that is just a waste of time. It's just a misunderstanding of how derivations work. So don't do that. So the crucial thing to keep in mind is the difference between what you want and what you have. I know it sounds basic, but nonetheless, people get confused about this all the time. Don't try to show something that exists on a premise. You have your premises. Don't try to show something on an available line. You have your available lines. Okay? Try to show something that you want that you don't have. Yeah?
Just go back to the derivation you just did.
Yeah, sure. Yeah?
On line 5, you have S. Why did you make a show line for S then?
Where did I do a show line for S?
Line 9, it's show S.
That was to close off this conditional derivation.
Okay, but can I just write, well, why did you write show S if you already had S? And you just said don't write show S.
Okay. You're technically correct, the best kind of correct. Yeah, no, actually, I didn't need the show line. Strictly speaking, you don't need a show. Remember I said you don't actually, strictly speaking, need the show line for the close off conditional derivation. So I could have just said, without that line at all, I could have closed this off. Show if R then S, assume R for conditional, 5 repeat direct derivation. So that would have been fine too. Yeah. So you're right that there are some circumstances where you want to write a show line for something that you have way earlier in the proof. For example, closing off a conditional derivation. Thank you for that. That is a slight wrinkle on what I just said. Yeah. Don't write a show line for don't write an unprompted show line. Sorry. Yeah. So here's the wrinkle. Don't write an unprompted show line for something that you already have. That was a prompted show line in the sense that I'd written a show line for the conditional unprompted, and then to just following my standard way of doing conditional derivations, I wrote the second show line. Okay. After that brief musical interlude, we are ready to move on. Unless there's any other questions about this stuff, because this is crucial. This is crucial stuff, and frankly, the stuff we're going to do for the rest of this class is like reasonably straightforward. So it's worth spending time on this if there's any confusions. Okay, let's plow on then. Okay, so last time we talked about conjunction, disjunction, and biconditional. So we introduced 3 new connectives to our system. That brings us up to 5 connectives. And we talked a little bit about how to symbolize those things. I think the symbolization of them hopefully is reasonably straightforward. Now we're going to talk about doing the derivations using these things. And before we do that, I just want to talk about 2 different types of rules. So that maybe this will be helpful to kind of keep it clear in your head all the different rules that we're dealing with. So the rules we're going to learn are each associated with a connective, and each of the rules that we'll learn either introduces the connective or eliminates it. You've seen introduction and elimination rules already. So here is negation introduction. So you start without a negation, and then using double negation, you introduce the negation. You introduce it into the proof. So before there wasn't a negation in that proof, after you apply the rule, there is one. Introduction rules take you from a state of not having the connective in that part of the proof to having the connective in that part of the proof. Negation elimination takes you from having the connective to not having it anymore. So introduction rules introduce the condition or the connective, elimination rules eliminate it. So for each of our connectives, there's going to be introduction and elimination rules. So this is just, and there's 3 connectives. I'm going to introduce 6 rules today. Each one is either an elimination or an introduction rule for one of the connectives. So just by way of hopefully helping you categorize what I'm about to show you. Okay, and here are the 3 connectives we'll deal with today: and, or, and if and only if, the biconditional. Okay, so as we go through these, I'm just going to show you again the truth table for these connectives, because the truth table helps to illuminate why the rules are the way they are. Okay, so these truth tables are in some sense definitions of the connectives, and the definitions of these connectives make it such that these basic rules work the way that they work. So recall, conjunction, and. This is true only in the case where both P and Q are true. Any other case, it's false. Very intuitive, yeah? Very intuitive. If I say it is snowy and cold, that's only true if it's both snowy and cold. If one of those fails to be true, the whole sentence turns out false. Okay, good. So that means that if I have the truth, it's true that it's snowy and cold, well, then it's true that it's snowy. And it's true that it's cold. Simplification is the rule that we do this with. So if you have a conjunction, this is the elimination rule for the conjunction. If you have a conjunction, you can get either part of the conjunct. Makes sense, right? It's nice to have a conjunction. A conjunction means you have 2 things. It's great. And you just simplify it apart. So here is the shortest possible derivation that I could think of that involves this rule. Suppose you've got premise 1, P and Q, and you're trying to show P. It is not a hard thing to do now. You say line 2, premise 1, simplify, S. That gives you P, and then you're done. Notice what you can't do. You can't just say premise 1 direct derivation. So if you want to show P, P and Q is some other sentence. It's not the same as P. You have to simplify it apart to use the parts. If you wanted to, for example, use P for modus ponens, so if you had if P then R, you still need to, you can't just cite premise 1 and say premise 1, this conditional modus ponens. You have to say premise 1, simplify and then you can use the P. You can't use it until you've broken it into its parts, but simplify is a really easy way to break it into its parts. Just a slight deviation from Logic 2010. Logic 2010, you can just put in S, and a little pop-up will say, okay, which side of it do you want? Or you could do the following. You could say SL for simplify left. So SL tells Logic 2010 which half of the conjunction that you want. And SR for simplify right. On the test, I won't mark this as wrong, but you don't need to do SL or SR. You can just write S and give yourself whichever half of it is the half that you wanted. Okay? Fairly clear? Okay. Yeah, so that's that. Okay, so that was the elimination rule for the conjunction. Here is the introduction rule for conjunction. It is adjunction. You adjoin them together. Adjunction, adjoin. So if you have, the only way to get a conjunction is, of course, to have the truth of both halves of it. So if you've got square and you've got circle, you can say square, circle, adjoin, and get square and circle. The thing to note here is that order matters. We will be picky about the order of these things. So square and circle is not the same sentence as circle and square. It's just one of the points at which we are going to be absurdly picky. One of many. Yeah?
Why?
Why? Because I said so. Okay. At least partly because Logic 2010 requires this. At least partly because at any point that you require human ingenuity or intuition or the ability to make sense of complex contexts, we're saying no to that. We're saying no, no, no. We try to the goal of a derivation, the reason why derivation is a mechanical process is that we're trying to break it down, break reasoning down into its smallest parts. And I've given you tiny little reprieves from that, like when I allow you to either pick not S or S as the result of your thing, but those are just tiny little exceptions. Everywhere else, we're trying to do reasoning in the smallest possible steps. So you as a sensitive, intelligent human can tell that square and circle adds up to the same thing as circle and square. But nonetheless, I'm going to require you to treat them as different sentences. Okay, so here's the shortest possible derivation with adjunction, ADJ. You've got P and Q as premises. You say premise 1, premise 2, adjoin. Again, Logic 2010 will ask you, a little pop-up will come up and say, what order do you want these in? You just click whichever order you want them in. When you're writing this stuff out, you just write it in the order that you want it. Supposing it's not in the order you want it, you can do the following. So suppose you want to prove, suppose you got Q and P and you're looking to prove the very controversial thesis P and Q. What you do is just simplify the parts apart. So premise 1 simplify, premise 1 simplify, and then just put them back together in the order that you want. It's not too challenging to get them in the order that you, given a conjunction in the wrong order, it is not super hard to get the conjunction in the right order. I don't think this will come up a lot, but yeah. Okay. Okay, so that was conjunction. Disjunction, the or statement. Recall that this is true in every case except when both parts are false. Okay. And that makes it an inclusive disjunction, not an exclusive disjunction. Inclusive disjunction means both can be true. Say this or that includes the possibility that both are true, or just one is true or the other is true. And this is going to matter for the rules that we're going to introduce for this. So Here's a lovely rule. I really like this rule. Addition. Given square, you can just add anything. Anything you want. And it's going to be true. That whole sentence is true. Square or circle. Circle can be the entire text of War and Peace. Square is, it is snowy, and circle is the entire text of War and Peace. And you can get that because you know if one half of it is true, that's fully sufficient for the whole thing to be true. That's what that truth table just told us. So you can add up. If you're trying to show a disjunction, all you need is one half of it, and you can add the other half. Is that obvious why that works? Okay, nobody's rushing forward to tell me that it's not obvious, so I'll move on. So here's the kind of thing that you can do. This is less than the most simple derivation, but suppose I wanted to show P or this weird thing, not X biconditional T or V. Okay. So I get myself P, and then I just add on the whole rest of it. That's it. You just add on it. Because you know that said line 3 is guaranteed to be true by line 2. We know that P is true. So we know P or literally anything you want is true. Lovely. I love it. It's very liberating. If you find yourself stuck in a derivation, you can just start adding things at random. It won't help, but it'll make you feel better. So, yeah. Okay. And again, Logic 2010 will ask you, little pop-ups will pop up. You type in the way that you want it. First, you select which order you want it, and then you'll type in what you want. When you're doing this by hand, you just write whatever you want, or whichever logically valid version of whatever you want. Okay. Here is the elimination rule for disjunction. Modus tollendo ponens. This one people actually get tripped up on kind of regularly, so this is worth sort of thinking medium hard about, or hard if you feel up to it. Okay, so you've got a disjunction. Suppose you've got square or circle. You know square or circle is true. You know the disjunction is true. What that means is that you know at least one half of that disjunction has got to be true. That's all you know. You don't, from that first line, you don't know which half is true. Maybe they're both true. Or maybe one is true or maybe the other's true. You don't know. But if in addition to that disjunction, you have the negation of one half of it, then what you know is the other half must be true. Right? If I've got square or circle, and I've got not circle, I know circle wasn't doing the work of making that disjunction true. Yeah?
Are we always assuming the stuff we're working with is true?
Well, we are assuming that the available lines you have are true. You assume the premises are true, and you assume the available lines are true. That assumption is safe because of our definition of validity. If it turns out that they're false, then the argument's still valid. Yeah? Okay. Okay. But yes, the answer to the question is yes. So you're assuming that your premises are true and your available lines are true. And the goal of a derivation is to show on the assumption that this is true that the conclusion follows. So that's why that's a reasonable assumption. Okay. So again, not the absolute shortest derivation we could do here, but suppose we're trying to show V. We've got P or V or X. If you have not P, that shows me that it's the V or X side of that triple disjunction that was doing the work of being true. And I've got not X, showing me that it's the V part of that disjunction that was doing the work of being true. So modus tollendo ponens. You cite the disjunction and the negation of some part of it. and then you get the other half. Not negated, but just the other half. Okay. And this is one of the points at which, I guess this slide is just to point out, this is one of the points at which we're going to be picky about the inputs. So there's no choice about the outputs of MTP. It always just gives you the other half. But you have to give me the double negated version of things. So you have to have, so not P or V, the negation of one half of that is not P. The negation of not P is not P. Okay? So this is, again, just like with modus tollens, we're going to be picky and demanding about the inputs to this rule. The input to the rule has to be negation and then whatever's on one side of the disjunction. Whatever it is, in this case, includes not P. So the negation of not P is not P. Okay. Okay. And just really quickly, and then I'll give you a break, the rules for biconditional. Biconditional. These are reasonably straightforward, I think, because the biconditional says it's true that it says if and only if, right? So if you have box biconditional circle, you can get if box then circle, and you can get if circle then box. The biconditional really just says that the conditionals in both directions are true. Both of those conditionals are true. So the rule, biconditional to conditional, says if I have the biconditional, I can get one half of that. I can get one of the conditionals. And you can pull apart both of the conditionals. So again, having a biconditional is nice because you get two things for the price of one. You get two conditionals that you can work with. Right? So the elimination rule for biconditionals, biconditional to conditional, BC. Again, really quick demonstration of this. I've got a biconditional in my premises. So I need to pull apart the biconditional into one half of it. If I'm doing a derivation, I will usually, as a matter of habit, pull both directions out of the biconditional. So I would say premise one, biconditional, give myself if P then Q. And then, I mean, if it's anything more complicated than this, I would do the opposite as well. Again, on line 3, I would say premise one, biconditional, and get if Q then P. Because I'm usually like not sure which direction I'm going to need. It doesn't hurt to have both. So as a matter of practice, like practical derivation strategy, I'll usually pull both directions out of a biconditional. But if I know exactly what I need, then I can just do one half. That's fine. Yeah? Right, so on logic 2010, you're going to say biconditional, conditional. Again, a little pop-up will show up and say, which direction would you like? And then you click on one or the other. At the end of this class, after the break, we'll do a bunch of examples. At the very end, I'll do one in logic 20, at least one in logic 2010 to kind of show you the commands or whatever. Okay. There's your question. And the introduction rule for a biconditional is conditional to biconditional, CB. That is, if you have the conditional in both directions, you can get the biconditional. That should make sense too, yeah? Because the biconditional says both directions of the conditional are true. If you have both directions, that means the biconditional must be true. Yeah? Okay. Just quickly an example. I made myself derive the two halves of the conditional, but just line 2, 3, and 4 are all you need to know here. Okay. And again, when you're doing this in logic 2010, a little pop-up, you say conditional to biconditional. a little pop-up will come up and say, which direction would you like this in? And you tell it which order you want the biconditional in. So again, order matters for the identity of a biconditional. And you can flip them around in exactly the same way we did with conjunction by pulling it apart and putting it back together. The best way to learn this is, of course, to just work through a bunch of examples. So that's what I propose to do just for the rest of this class. We're just going to do a bunch of examples. Yeah, here we go. OK. Zoom in a little. Right. So same as always, we're going to start with a show line. We're going to show Q and not T. I will just, as a matter of course, do this assume ID, but that's really not going to be useful to us just yet. When we get some derived rules, line 2 would be very useful to us. The negation of a conjunction turns into something else with De Morgan's law. But since we're in basic rules right now, that's probably not going to be useful, but I'll do it anyway. OK. Now, what do? Standard, absolutely standard sort of like, OK, actually, before I start surveying my resources and looking for what I do, let me talk a little bit about this conclusion, because how are we going to get this conclusion? Basically, let's do the backwards looking thing a little bit at the beginning here. How am I going to get to the conclusion Q and not T? Well, I'm going to have to build that somehow, right? I'm going to have to adjoin together Q and not T. Yeah? So at some point, I will have to have derived Q, and I will have to have derived not T, and then I'll have to just put them together, and that'll be my conclusion. So this is going to end with, I predict this is going to end with a direct derivation where I've adjoined together Q and not T. OK? So that's how this is going to end. That's our end game. Now let's just start from the beginning again, see what we've got, make some moves, see if we can get, just by doing some moves, if we can get Q and we can get not T, then we're done. Right? OK. So what do we got? Well, we've got not P, and we've got if T, then P. That looks hopeful. Right? So premise 2, premise 3, modus tollens, good old modus tollens, giving us not T. Hey, that's one half of the thing we wanted. Great. Things are going great. We're halfway done. OK, not really. OK, now what? Now we want to do something with, for example, not P and P or Q. Right? Because what do we say? We said if you've got a disjunction, this is a disjunction, we know that P is true or Q is true, but according to premise 2, P is false. Well, that means that Q must be true. So if I say premise 1, premise 2, MTP, modus tollendo ponens, that gives me Q. Right? If I have the negation of one half of a disjunction, so I have not P, I know this is false, meaning this must be true. Things are going really well in this derivation. We're really clipping along. This is great. Because we've got on line 3 not T. That's good. That's one half of the thing we wanted. And on line 4, we've got Q. That's the other half. Oh my God. This is going great, you guys. I have a really good feeling about this derivation. OK. So now all we have to do is put them together. Now all we have to do is put line 3 and 4 together. We have a rule for that. Our introduction rule for the conjunction, which was we're going to join them together. We're going to adjoin them. So we're going to say line 3, line 4, ADJ, adjoin. And we'll just put them in the order that we want them, Q and not T. And that's it. We did it. So on line 5, we did a direct derivation. Yay. Yeah. Sorry, I can't hear you. No, I said the opposite. I said the opposite. You're allowed to, when you're joining, you're allowed to put it in whatever order you want. Yeah? So order matters. Order matters a lot. So if I had instead written the following, if I'd said not t and q, well, I'm not allowed to close off the derivation using that. That's no good to me. But given the exact same inputs, 3, 4, 80j, I can also derive q and not t. So again, Logic 2010, a little pop-up will come up and say, which order would you like to adjoin these in? And you can you click on whichever order you want. When you're writing your derivations, you just put it in whatever order you want. And maybe what you're asking about is the order of these, 3 and 4. And those don't matter either. You just put them in whatever order you want. So I equally could have said 4, 3 adjoin and given myself either one of these. Yeah, there's 2 hands here. Yeah.
Why do we need the
Oh, sorry. There was 3 hands all the way in. So as I said at the beginning, the ID is useless. But I do it because I want to be approaching these derivations in as mechanical a way as possible. That is, if I see something, if I'm trying to show something that's not a conditional, I'm going to start an ID. Do I know that's going to be useful? Well, no, because I don't know how the derivation is going to end yet. So that's a kind of automatic move. It's a kind of, I want to be acting a little bit like just doing a bunch of stuff automatically so that I don't have to think, try to reduce the amount I have to think about these things. So that's why I did an ID there. And it did not help me at all. So line 6, direct derivation, box, cancel. Other questions? So what happened? That was a bizarre confluence. Three people exactly in a row had the same question. You all seem to have been satisfied by the same answer. That was weird. That was weird. Okay. Yeah.
And so if we include these useless lines, will you be confused when you're grading?
No. The people grading these are PhD students in philosophy. They can. The suggestion that a PhD student in philosophy would be confused by something that's irrelevant really doesn't understand what philosophy is like, because we got a lot of irrelevant stuff going on. We have a lot of irrelevant stuff, and we just swim through it. That's the ocean. Irrelevancy is the ocean in which a philosopher swims. It's wonderful. So, yeah. Okay, yeah. Good. So that would not have been wrong. So I could make, if I was looking to make myself feel like I hadn't made a useless move, I could do the following. I could say line 2, line 6 ID. That would be a uniform derivation. So line 6 is indeed the exact opposite of line 2, and I could close off. I could have closed it off. It's just as good, just as accurate to close this off with an ID rather than a direct derivation. Yeah.
How is it correct? Because the only way we got a contradiction was to assume the opposite we wanted to show.
So this was not a direct derivation. This is an indirect derivation. But if I'd done 6 DD, then I didn't use line 2 at any point. And besides, any time that you have a line that exactly matches the show line, then you're allowed to use direct derivation. Even if it looks like maybe you needed the indirect or whatever. Yeah. Good. Okay, let's do another. Here we go. Here's one. Okay. Again, we're going to try to show a conjunction. Oh, okay. Is this the same one as before? No, this is a different derivation. And once again, I'll do the assume ID just because I'm a creature of habit. It's good to have that habit because, again, line 2 will be useful to us. As of Wednesday, line 2 will be potentially useful to us. Right now it's useless, but that's fine. Okay. So I know that eventually I'm going to have to derive not Q, and I'm going to have to derive T. Not super obvious to me right now how I'm going to do that. So like thinking backwards isn't really a helpful perspective right this second. So let's look forward. Let's ask ourselves, what have I got? Let's try to make some moves. Let's try to do some things. So for example, premise 2, that looks promising. So I can say premise 2, premise S is not a thing. Premise 2, simplify. I get P. That's good, right? So I simplified off. This whole thing is a conjunction. This is the major connective. So I can simplify off P. I can likewise simplify off, if not T, then not S. It's also premise 2, simplify. Okay? The other thing that I'm likely to do here, premise 1. So this takes some parsing. I hope that if you're worried at all about your capacity to parse, I suggest you do a bunch of those parsing problems. Just crank through them. They're not, once you get them, they're easy. But so we got to parse premise 1. We need to figure out what the major connective is. So what's our bias here? We got a bias that we're going to revert to. We got blatant favoritism towards the biconditional, right? So if you didn't know that we had this convention, it would be unclear whether this said biconditional and S or biconditional P biconditional this thing. And because we have this convention, it's always going to be the second thing. It's always going to be, this is the major connective. Yeah? Okay, so biconditional, nice to have a biconditional because that gives you two things. And again, I'm not going to spend too much brain power right now trying to figure out what exactly I'm going to need. I'll just pull it apart. I'll just pull both directions out of it, just so that I have it laid out in front of me. And once it's laid out in front of you, it's cognitively easier to deal with. So I'm going to do both directions just to reduce the strain on my working memory. Is that a hand up there? Yeah. Yeah. Sorry, could I? Oh, I see. So you're asking about, so the original show line is show Q and T. Could I do show not Q, show it, and then show T? Yes, you absolutely can do that. Yes, you can. That's a perfectly valid way of approaching something like this. So good, good. Okay. So let's pull apart premise 1. So I'm going to say premise 1, and I'm going from a biconditional to a conditional. So BC, you start with the biconditional, going to the conditional. You say if P, then not Q and S. Strictly speaking, I don't need to have those brackets, but again, I'm going to write them in because I'm making it easier for myself. I'm reducing the load on my own working memory. I'm helping myself out by writing those in. So that's why I'm going to do that. And then just the same, then P. That's also premise 1, biconditional to conditional. Okay. So all I've done so far is just looked at what I've got and say, oh, okay, both of those premises have potentially useful stuff in them, but I need to make a couple of moves to make it useful. I have to simplify apart the conjunction, and I have to pull the conditionals out of the biconditional to be able to do stuff with them. Okay, so I'm just unpacking. This is like, I have a bunch of resources. I just need to unpack them, lay them out in front of me, and get a good look at them and see what I can do. So now I'm ready to kind of make some moves with these things. So here's a move I should make. I got P, and I got if P, then this thing. Great. So I'm going to say line 3, line 5, modus ponens. Get myself, if not, or sorry, not Q and S. Okay. Now I have a bit more unpacking. Having got that, I have a bit more unpacking work to do. I can say 7 simplify, get not Q, and 7 simplify, get S. Okay. So line 8's great. Line 8's a really good one to have. Why is line 8 so good? Yeah, that's half of the thing I was trying to show. So that's really good. It's really nice to have. Okay. I'll zoom out a bit, sorry. Okay. Now I just need T. And then I can put them together and it'll be done. So now I'm switching momentarily. I'm switching from the forward-looking. So far, we've just been doing the forward-looking, like what have I got, and can I make some moves with it? Let's take 1 second and do the backwards-looking thing where I'm like, where am I trying to get? Well, I'm trying to get Q, not Q, and T. I got not Q, now I just need T. And now I just look for T in my available lines. Say, well, where does, instead of just continuing to just do stuff at random, which what I've been doing so far, now I'm like, where's T? How do I get T? Oh, okay, T shows up. Here's T in available line. It's on line 4. If not T, then not S. Okay. I've got S down here. So if I say line 9, double negation, and you do need that double negation if you're going to use a line 4 modus tollens, right? So this gives me not 9 double negation gives me not S. Modus tollens gives me not T. Or, if you prefer, you can give yourself the version that you want. Just give yourself T. Again, recall our rule. The inputs have to match exactly. We're picky about inputs. The outputs, you can give yourself the double negated version or the not double negated version. Okay. So we're just about done. That was the other thing. Recall, that was the other thing that we were trying to get, is T. So we just put them together. We say 8, 10. We're going to join them. We're going to adjoin them. Adjoin, not Q, and T. Done. Line 11, direct derivation. Draw myself a prettier line for that pretty derivation. How's that? How do we feel about that? So one of the wrinkles that we've added here is the notion of unpacking your resources. It's not really a thing we had to do before, but with the rule biconditional to conditional, that's where you have a biconditional and you need to unpack it to use it. Similarly, the simplify rule, if you have a conjunction, you need to unpack it to use it. You need to take it apart into its parts, and then the parts are useful. So, questions, or do you want to do another example? Okay, let's do another example. All right. All right. We're going to show S. Anytime I write a show line for something that's not a conditional, I'm going to start an indirect derivation. So not S. I'm going to assume that for indirect derivation. Okay. Nothing Nothing jumps out at me here as stuff that's interesting or helpful except the following. I got not S. Well, I can do modus tollens here, right? So line 2, premise 3, modus tollens. And that'll give me, it's not a pretty thing to get. It's not the case that P or Q and T. Oof, okay. Once again, that's the sort of thing that'll be more useful later. All right. Let's do a bit more unpacking. That's one move you can make. Kind of a beast of a line. You know, there's a lot of parts to that. Here's some unpacking we can do in premise 2. So premise 2, it's a conjunction, so we can simplify not R, and we can simplify T. Okay. Again, I'm not really doing I haven't got a grand strategy right. At the moment, I'm going to admit to you, I do not have a grand strategy for this derivation. I'm just trying stuff and seeing what unlocks for me. Maybe a grand strategy will emerge as I do a bunch of stuff, but maybe I'll just stumble on a solution and then we'll be done. Okay, so now we got not R. That's useful with premise 1, right? So we say premise 1 and line 4, modus tollendo ponens, that gives me P. That's cool. That's good. I got P. So, given P, what do you think we should do? Yeah. Sorry, antecedent with the third premise? Aha, okay, so good. That's right. So given P, I can get P or anything, right? And P or QNT is the antecedent of this conditional. So again, recall our blatant favoritism for the conditional. This is really saying this. So if I say P or Q and T, I can get that from line 6, add. My favorite rule, add stuff. Yeah? So by adding Q and T, I've built the antecedent of this thing, which means I can say line 7, premise 3, modus ponens, and get S. Which is great. That's the thing we're trying to show. Now there's two ways of closing this off, equally good ways of closing this off. We can say line 2, line 8, indirect derivation, and call it done. Or we can just say line 8, direct derivation. Either one of those, perfectly good way of finishing this derivation. Yeah? I'm sorry, I think. Oh, good, good. Yeah, you could also have done that. Very good. So that would have actually saved us a line. So we were already done here. 3, 7, ID. Because that is the negation of that. Very good. A third way to close this derivation off. Recall the rules that I've set for marking these derivations. If you get from beginning to end by following all the rules, you get all the marks. So there's no bonus points for writing a slightly shorter derivation. And any one of those 3 ways would have gotten full marks for this derivation. So just in case, people get People get mildly disturbed and anxious when there's more than one way of getting the right answer. They're like, which is the best way? Doesn't matter. There are equally good ways. I'm sorry, I often struggle to hear your questions. I think I have at least partial hearing loss. I always constantly meaning to get that checked. Too much loud music, I think. Okay. If there's no questions about this, we can move on. Yeah.
So as for line 3, can we just unpack that big bracket? So you say it is a conjunction right now, and we can unpack it sorry.
It's a disjunction right now. Okay, so what you're asking about is one of the rules that we'll introduce on Wednesday. So this is De Morgan's, and many of you have been tempted by this. So if you have not the case that this thing, then you can use De Morgan's rule to say not box or not circle. There's actually a bunch of versions of De Morgan's. So we'll introduce that on Wednesday. That's one of our derived rules. You're allowed to do this on 2 of the derivations for the test, but not 2 of the other ones. So there's derived rules and basic rules derivations, and sometimes we'll allow you to use the derived rules, and sometimes we won't. Yeah. Okay. Okay. All right. Yeah, this thing's long. Okay. Okay, so this is a nice example, however, because it's an example of trying to show a biconditional. And here you do need to think about what you're trying to do a little bit. So to show a biconditional, suppose I want to show box biconditional circle. What I need is box conditional circle and circle conditional box, right? So basically, I've got 2 things I want to show. Once I've shown them both, then I can put them together using conditional to biconditional. Okay, so that's going to be anytime the show line is a biconditional, basically you're just looking at 2 derivations and then combining the results of those 2 derivations together. So we'll start with, you do have to start with the original show line, not Q and R. But I'm going to kind of just immediately start trying to show 1/2 of it. So I'm going to say show if P, then not Q and R. And then I'm going to do this whole derivation. So that would be this thing. And then I'll write another show line for not Q and R, then P, try to show that, and then put the results together. This is going to take a while. Settle in. All right. So trying to show a conditional, just start a conditional derivation. We got P. We're going to assume that for conditional derivation. I'm going to show not Q, and R. Good. And I'll do just as a creature of habit, I'll do an assume ID here. Again, I don't think it'll be super useful. Okay. So, what have I got? I have line 3, line 5, and my premises. Well, that doesn't leave me much. Line 5 is probably not going to be incredibly useful. The one exception, so often it's useful to write a show line to try to generate a contradiction. If you've just assumed ID, that show line is just the same as this show line, so it's probably not going to move you forward very far, right? So this is not a thing. This is not going to be useful as a contradiction generator just because it's the thing that we got by assuming ID. So, because if I had this, then I'd be fine. This derivation would be over. So 3 is more or less, 3 in our premises are more or less the only thing we've got going on. This premise doesn't include P at all, so that's not super helpful. This one includes P, however. So let's try to unpack this. So we'll say premise 1, and I'm only going to unpack 1/2 of it right now. I'm going to biconditional to conditional, and I'm going to say if Q, then not P. Why did I do that half of it and not the other half? Because I know I have P. So if I say line 3, repeat, double negation, gives me not P. And then I can say 6, 7 modus tollens to give myself not Q. Okay. And then not Q is kind of useful because that's the other thing here. So we can say line 8, premise 2, modus ponens, get R. Hey, that's good. That's super good, because remember what we were trying to do here. Again, so you have to, if you never flip back to the backwards looking where was I trying to get, you're going to be in trouble. So you kind of have to be able to flip back and forth between these two perspectives, because it's time now to flip to the backwards looking perspective, because I now have that thing that I was trying to show here. So I've got, if I put together line 8 and line 9, so 8, 9, adjoin, I get not Q and R, which is the thing I was trying to show. You can also save yourself one line by just going DD on that line. Okay. Great. So showed the consequent of this thing, meaning that on line 4, I did a conditional derivation. Great. Things are going well. So what did we do there? We just finished doing 1/2 of our plan to derive this biconditional. The plan to derive the biconditional, derive both directions of it, and then put them together. We've done 1/2 of that. Now it's time to do the other half. Yeah? So again, this is where, so you can't always get through a derivation just blindly doing whatever looks possible. You're going to have to start thinking about the structure of derivations as well. So this is my plan for my derivation. This is the structure of this derivation. So now I recall my plan. It's going well. I did half of the plan already. Now I just have to do the other half. I have to show if not Q and R, then P. Okay. Do try to write your numbers right. Okay. So now we're going to assume not Q and R. Assume for conditional derivation. Line 14, we're going to show P. Right. Zoom out a little. Oh. Okay. Is that still, this is reasonably legible, yeah? Okay. So, line 15, we'll assume, or sorry, we'll give ourselves not P, assume ID. Line 16. Actually, you know what I'm going to do? I'm going to start back up here. So, line 16. Okay, what do we got and where are we going? We got line 13. We got line 15. Please notice what you don't have. You don't have any of this stuff anymore. Yeah? These are all boxed lines. These are no longer available lines. You cannot use these in your derivation anymore. Okay. So what should we do? We've got not P, we've got not Q and R. Let's do some light unpacking just to get warmed up. So not Q, that would be line 13, simplify. We've got R, 13, simplify. Okay. Well, we got not Q. Well, that'll give us, so we could do the following. We could say line 16, premise 2, modus ponens to give ourselves R. We already got R. There's not much point in that. So what about this stuff? We've got, let's do not P, then Q. That is premise 1, biconditional to conditional. 19. And that's kind of nice because we've got not P. So we can say on line 15, line 18, modus ponens to get Q. And that's very promising indeed, because it contradicts line 16. It's very good. So we've got line 16, line 19, indirect derivation. We can cancel and box. Okay, now things are really going well, because we can say that we did this conditional derivation. Because on 14 CD, box and cancel. Okay, so now we did the other half of it. We derived one half of the biconditional. We derived the other half of the biconditional. Now it's just a matter of putting them together, and we're done. So we have on line 2, because this show line is canceled, none of this is available, but because this show line is canceled, line 2 is available. Similarly with line 12. So we're going to say line 2, line 12, conditional to biconditional. I'll just give myself the order that I want. P, biconditional, not Q, and R. And that is a direct derivation, DD. Ta-da. Okay, that is the longest derivation we've done so far. It's a lot to keep in your head. It really is. If there's no questions about, are there questions about this? I do have, yeah.
For line 16, should you have repeated the not Q and R before we get back?
Yes, thank you. Yeah, 13R, 13R. Yes, thank you. Okay, there's one more thing I want to show you though. I want to show you this same derivation in Logic 2010 so that this stuff that pops up will be familiar. Okay. Here it is, hooray. So, show conclusion, as always. There's a nice command that you can type in to make it show half of a conditional, show cond, and this thing will pop up. Hey, which half of that biconditional do you want to show? Oh, okay, well, I'll show this half. Assume CD, show consequent. I don't have to assume ID. So premise 1, biconditional to conditional. And again, it'll give us this pop-up. Which half of the biconditional do you want? Because I know which half I want, I'll do this one. 3, repeat, double negation. 5, modus tollens to give us not Q. And then line 6, premise 2, modus ponens to give us not R. 6, 7, adjoin. Okay, once again, it's going to give you a pop-up. And it asks you which version that you want. You just you have to remember which version it is you wanted. click on the right one. Okay. So 8 direct derivation. One more thing I'd like to show you, or sorry, and then 4 conditional derivation. One more thing I'd like to show you here. You can click on these arrows and collapse this all down. So these derivations can get long, and because all of this is boxed, you're not allowed to use any of this anymore. So none of this is relevant to your derivation anymore. You might want to simplify things by just collapsing it down. Show conditional. This time I'm going to show the other half. Assume CD, show consequent, assume ID, premise 1, biconditional, conditional. Wow, look how much easier it is on Logic 2010. Okay, so 12, repeat, simplify left. 16, 17, ID. Done, 13, CD. Okay, and again, I can collapse this down, and I don't have to look at all this mess that I've created for myself. Now, 211, conditional to biconditional. Okay, and it's crucially important that we get it in the right order, but this is in the right order. 20, so 20, direct derivation. We're done. Okay. One more thing to show you, the add function. So if I said 20 add, it gives me the following pop-up. So I want to choose which side of it I want to add to. And then you can just type, so click here, and you can just type anything. P biconditional, R, or Z, and, or X. Hooray, I made myself a big weird thing. Hooray, good for me. Okay, so that's just to show you the stuff on Logic 2010.